All right, class, here we are in the second chapter of the respiratory system, part of our course, chapter 18. We will go through the whole chapter. We're also going to incorporate the gas laws from chapter 17 of the textbook. All right, so as you know, our body needs oxygen, but also just as importantly, we need to get rid of carbon dioxide, because a buildup of carbon dioxide in our body can cause us to become acidotic, but it also, well, hopefully it would trigger the compensatory mechanisms to correct that. That's not normal to have a buildup. So hypoxia with the ox in it, less ox, is too little oxygen, where hypercapnia is an increased amount of carbon dioxide. It is possible to have a normal oxygen level with hypercapnia and vice versa. So I don't want you to put them in mutually exclusive categories, because they absolutely are not in that category. Many times a buildup of CO2 is related to the respiratory effort. And I can share this with you from my own personal experience of having asthma. I've suffered with asthma for most of my adult life. I've actually had to be intubated twice because of respiratory failure. I've very, very rarely become hypoxic. I'm able to keep my oxygen level good, 95% or above, outside of the setting of an infection. But when I typically have my average asthma attack, I'm saturating at about 98 to 100% oxygen in my blood. But what is a problem is that I'm having to work so hard to keep my oxygen level at a good level that I build up CO2 in my body. And then that causes a condition called acidosis, where the bloodstream becomes acidic, because I've exceeded the buffering capacity of the blood by having too much CO2. So I share this with you because both of the times when I was intubated, my oxygen saturation was great, but my CO2 built up so much that it caused failure in parts of my body. So, and I do know from having asthma and being seen in the emergency room setting that unfortunately this is a misconception. I've had many triage nurses tell me, oh, your oxygen saturation is fine, you're doing great, including the 2 times when I was intubated. I would argue I was not doing great those 2 times. So it's important that we do whatever we can, right, as future health professionals, to educate people, but also to protect ourselves. So if you have anybody in your family with respiratory challenges, this might be a worthwhile conversation to have with them. So in order to avoid both hypoxia and hypercapnia, we do have multiple corrective mechanisms, but they respond to three variables: oxygen, the partial concentration of oxygen or the pressure of oxygen, carbon dioxide, and then the third is pH. So our respiratory system is able to sense and figure out what to do with changing levels of any of these three variables. So in my case, it was an increase in carbon dioxide and a decrease in my pH that really signaled the alarm to where my body started to need, more intervention than it could do on its own at those times. Certainly, I remember one of the times when I was intubated, I was awake at the beginning of the procedure. The second time they put me out right away, but it's very disturbing waking up and being in that situation. All right, so let's tie us back to what we learned in chapter 17 about the 3 areas or levels of gas exchange. So this figure is really showing us the process of gas exchange, but let's add in those three levels of exchange. So the first happens between the atmosphere and the lungs. That's exchange level 1. So that would be happening in the alveolar sacs. The second level of exchange is between the lungs and the bloodstream. So the transference of the molecular oxygen out of the alveolar sacs following its pressure gradient into the blood vessels, where it's then pumped around the body to every single part of the body. And then transfer level 3 is the level between the bloodstream to the tissue. So that would be the final stage. So our oxygen gradient decreases as we move through, in this figure, steps 1, steps 2, and steps 3. So our oxygen gradient is highest in the atmosphere. It is lowest in the tissues. That is opposite from the carbon dioxide differential. It is highest at the level of tissue or cells that have just undergone metabolic, or I should say, have just undergone cellular respiration. So they're producing CO2 as a product of cellular respiration, which then moves back to the bloodstream and then back into the lungs so it can be exhaled out in the form of carbon dioxide. So oxygen actually travels quite a bit differently in our body than does carbon dioxide. Oxygen travels within that red blood cell. Carbon dioxide, well, a tiny bit of it can travel there, but most of it travels actually dissolved in our blood as a chemical. So looking at the normal values in the arterial versus the venous side, we have the partial pressure of molecular oxygen, of carbon dioxide, and then the pH. So oxygen is higher in the arterial side. Well, good, it needs to be since it is supplying those tissues, but then it should drop off in the venous side after it has moved into the tissues and the tissues have consumed it. Oppositely, the CO2 is lowest in the arterial side, and it's higher after the cells have gone through cellular respiration and it's been picked back up in our veins. The pH is lower, and this may not look like much of a difference, 7.4 to 7.37, but it's actually quite a profound difference. We don't need to see very big changes in the linear numbers of the pH scale to know that there's a big impact. Remember that every one number, so changing from pH 7 to pH 8, that is a factor of 10 times a difference in pH value. So it may look small to us on this scale, but it's bigger than we may realize. All right, so this is the figure that comes out of chapter 17 that summarizes the gas laws. And so really this is what I want you to focus on. And the reason why I'm not digging too deep into this now is much of this we've already visited when we talked about the movement of molecules through our circulatory system and through other systems. You now understand about diffusion. And we know that, and we're starting to understand about pressure gradients. So what the gas laws tell us is that the total pressure of a mixture is equal to the sum of the individual gases. So if we're looking at the total pressure of the air, it would include oxygen, it would include carbon dioxide, argon, nitrogen, water vapor, all of the things that are in there. Oh my goodness, my kitty is outside again. Let me just pause you for a moment. Excuse me. Sorry about that. My youngest kitty, his name is Dirtball. He pretty much only goes outside when I'm lecturing to purposefully interfere with my attention. There's a window right beside me and he'll come outside. He literally has to get on the fence in the backyard, jump on the roof, climb over the house, come off the roof and jump outside. But that's what he does. He's very persistent, but he'll come and sit right outside. And I don't like him out front. He's not supposed to be outside. So I apologize for the interruption. So the total pressure of a gas mixture equals the sum of the individual pressures associated with each of the gases in that mixture. If we are wanting to look at the partial pressure of a gas in dry air, we simply take that gas's contribution and multiply it by the atmospheric pressure. So the pressure of the gas is equal to the atmospheric pressure times whatever percentage of the gas we're looking at. If we want to calculate the partial pressure of a gas in humid air, such as in Florida, then we need to consider the pressure that comes from the water vapor. We would actually need to remove that because that is an added factor in the air. Now, gases, just like other material, they follow a gradient from higher pressure to lower. That facilitates bulk flow. I mean, without it, there would be no such thing as bulk flow. And then finally, if the volume of a cylinder changes, say we have a beaker that holds 1 liter, but all of a sudden it expands and it holds 5 liters, well, then we've got a proportional change. And we can use Boyle's law to figure that out, where the pressure 1 in volume 1 is equal to pressure 2 in volume 2. It's a proportional change, but it changes inversely. So the volume of the gas in a container is inverse with its pressure. And that's because, for example, in order to solve for pressure 2, we would have to divide out volume 2 from both sides of the equation. So breathing is simply a different way to think about it. It is the input of the bulk flow that gets air into our lungs as well as out of our lungs. We don't want to think about it as only being into our lungs, because bulk flow is the distribution of material following a gradient. So there is a gradient of carbon dioxide as well moving out of the body. We saw that in that figure just a moment ago. It is 46 at the tissues, but 40 in the atmosphere. So our individual gases do follow their own partial pressure gradient until they hit equilibrium. Just like we learned about with osmolarity, everything follows its own gradient, but there is an impact of the sum of all the materials on either side of the membrane. So our total pressure of mixed gas is equal to the sum of all of those individual pressures coming from each gas alone: oxygen, carbon dioxide. There is we do see gas exchange right between the alveoli and the blood. That is gas exchange level 2. And we make the assumption based on scientific data that this is a very efficient process, where the oxygen that comes into the lungs, into the alveolar sacs, it will move into the blood, unless we have a problem like restrictive airway disease, where there's fibrosis of the alveolar epithelial, which prevents the diffusion of that gas. But in a healthy situation, it is very efficient. So we take it at 100%. So the pressure in the alveolar air is greater than the pressure in the blood. We're establishing the gradient. What's higher out here is the pressure in the atmosphere for oxygen. If we look at carbon dioxide, the pressure of carbon dioxide in the blood is greater than it is in the alveolar air. It is inverse because of the different gradients. Oxygen is higher in the atmosphere. It decreases as we get to the tissue, where carbon dioxide is the most concentrated at the level of the tissue, and it decreases as we move to the atmosphere. So at the level of the blood and the tissues, again, the pressure of oxygen is higher in the blood than it is at the tissue. It needs to be, or else we don't have diffusion anymore. And then the opposite for the carbon dioxide. It's highest in the tissue. So let's look at that again. This is the same figure we've looked at now, I think a total of 3 times, including in chapter 17. But now we've got the pressures associated with air, dry air. We're not in Florida now. And then we've got the pressures of oxygen, molecular oxygen, and carbon dioxide. So in the dry air, the pressure of molecular oxygen is 160 millimeters of mercury. So that is exchange level 1. At exchange level 2, it's decreased to 100 from 160. And it stays at 100 as the oxygen travels through the bloodstream bound to hemoglobin, because hemoglobin is really good at its job. But then it drops off from 100 to 40 at exchange level 3. So our gradient of oxygen is highest in the atmosphere and decreases as we move to the tissues. Oppositely, carbon dioxide is highest at the level of the tissues. It's about 46 millimeters of mercury. But as we move into the bloodstream, it's still about 46. It's not until we get to the exchange between the blood and the alveolar sacs, so that's exchange level 1, where we see a drop off in the pressure of carbon dioxide. But now look how much it drops off when we move to the atmosphere. There's a huge difference. So we do see changes in the partial pressures of each of these gases as we move through the body. But we still have the gradient, right? It's still highest for oxygen in the atmosphere, lowest in the tissue. Carbon dioxide is highest at the tissue and lowest at the atmosphere. So I would like to just point out that the gradient for carbon dioxide is not as strong as it is with oxygen. 46 for carbon dioxide to 40. Whereas for oxygen, we're 160 going all the way down to about 40. And this does have to do with the fact that most of our carbon dioxide travels dissolved in our bloodstream, as opposed to bound to hemoglobin. That's what hemoglobin transports oxygen. That's the job of oxygen. All right, so looking at a zoom in of the different layers that must be bypassed by those respiratory gases. So we've got our alveolar space up top in white, and then the epithelial layer. The basement membrane is in gray still. And then we have the epithelial layer of the blood vessel, the plasma, and then finally the epithelial layer of the red blood cell itself. So the difference, that strong gradient in oxygen facilitates the diffusion of oxygen into the bloodstream. Again, it goes from about 160 in the atmosphere down to about 40 at the level of the tissue. So that's a pretty sharp gradient. And then once the oxygen is bound onto hemoglobin, well, it's safe there. Hemoglobin is efficient at its job of transporting oxygen. All right, so let's look at how oxygen is carried in the blood, and then we'll look at how carbon dioxide is carried in the blood, because they are different. Now, the majority of oxygen is bound to hemoglobin. So we call this oxyhemoglobin. About 98% of oxygen travels in our body bound to hemoglobin within the red blood cell. Only about 2% of it is dissolved in the plasma. All right, just about 2% of it. Now, in order, so let's go through the whole process. So oxygen needs to move through the various barriers out of the alveolar sac into the blood vessel, and then finally into the red blood cell itself, where it binds to hemoglobin. And it's transported very efficiently through the body this way, But in order for the oxygen to move into the cells itself, it has to disassociate from hemoglobin so that it can diffuse across the various layers and enter cellular respiration. So 98% of oxygen travels bound to hemoglobin within the red blood cell. We've seen this structure before. Hemoglobin has 2 alpha chains, it has 2 beta chains, and then 4 of these heme groups that are centered, built with an iron core. Fe is the atomic symbol for iron. So this is a porphyrin ring, this whole structure, and there are 4 of them for each hemoglobin. What we're going to get to is this concept of cooperativity. Now, each hemoglobin molecule can bind up to 4 oxygen, but there's many hemoglobin proteins within a red blood cell. Plus, we've got the neighboring red blood cells right beside, right? So what cooperativity does is it facilitates maximum binding of a single hemoglobin before another hemoglobin is filled up. In other words, we get 4 oxygens bound to 1 hemoglobin, preferentially, prior to separating out those 4 oxygens into 4 different hemoglobin groups. So we have a number of factors that facilitate the binding of oxygen to hemoglobin. So that happens when our plasma concentration of oxygen is low. So we could measure that with our percent oxygen. Or rather, I should say that we can determine the amount of oxygen by looking at the amount that's bound to hemoglobin. But then we can look at, well, how much hemoglobin do we have? And we can figure that out based upon the number of red blood cells and what the total quantity is of hemoglobin within that red blood cell. And we know that there's 4 binding sites per hemoglobin molecule, but red blood cells have many hemoglobins. So we can determine the amount of oxygen bound to hemoglobin. Again, that's about 98%. Now, the affinity changes. Hemoglobin has an affinity for oxygen that changes under different factors. So the affinity for oxygen decreases when there is an increase in carbon dioxide in the interstitial fluid. Because, oh my gosh, dirtball's out there again. He's just going to have to wait this time. The reason why is now we need to get rid of that CO2 out of the interstitial fluid. So hemoglobin is going to pick it up to help get rid of it. But if there is a decrease in the pH, we also have an increase in the affinity for oxygen. And that's because there's a relationship between pH and carbon dioxide concentration. When the temperature increases in the tissue, we also see a difference in the affinity for hemoglobin to oxygen. So let's look at that. The top graph is looking at the effect of pH. And all of these figures, we have the partial pressure of molecular oxygen along the x-axis, and then the percent hemoglobin saturation on the y. Now, the yellow line is at a pressure of, is at a pH of 7.6. The center brown line is 7.4. So that's close to our typical homeostatic value. And then the green line is 7.2. So as we become more acidic, there is a decrease in the hemoglobin saturation by oxygen. And that's because hemoglobin is going to start to pick up the carbon dioxide in this example to get it out of the bloodstream. If we look at, oh my gosh, he just jumped on the roof again. I'm sorry. I'm just worried about my kitty out there. If we look at a variation in the temperatures, we've got 20 degrees Celsius all the way up to 43. And of course, 37 is our average body temperature. So when we are warm, there is a decreased affinity for oxygen. Looking at the effect of the pressure of carbon dioxide, we've got 20 millimeters mercury of carbon dioxide, then 40, and then the red is 80. So when we are at the lowest partial pressure concentration for carbon dioxide, we have the higher and sharper slope for the oxygen binding to carbon dioxide. And then finally, there's a chemical called D3-DPG. And what this, and we see the same pattern here. So normal is the purple line, none is with carbon is in the blue. And then when we've added extra of it, that's what the red line is. And we see a distinct difference between these. So these are some of the examples of different variables that facilitate the binding, the maximum binding of oxygen to hemoglobin. Okay, so let's dig deeper. Now, maximum binding of oxygen to hemoglobin, but there is a relationship, as we saw, with carbon dioxide and with pH. And this is why. When carbon dioxide is mixed with water, in other words, in our body, because we're mostly water, we produce H2CO3, which then disassociates into the hydrogen ion and the bicarbonate ion. This is acid. So another way of interpreting this is when we have too much CO2 in our body, we become acidic. And this is exactly what happened with me in the cases where I've had severe asthma attacks, and the 2 times where I was intubated, my oxygen concentrations was decent, but I built up so much carbon dioxide that my bloodstream became acidotic, and then that led to other problems. So fortunately, it's easily reversed with adding buffers and potassium. So this reaction, we can push either way. It's reversible due to the law of mass action, but if there's more carbon dioxide, it's going to push this way. If there's less carbon dioxide, then it pushes the other way. So when carbon dioxide is in high concentration, we are going to produce acid. And there is the possibility that that could overcome the buffering capacity of our body in a person that is having respiratory distress. All right, so now let's look at how carbon dioxide is transported in the blood. It's a bit different than oxygen. So again, oxygen, 98% of it is bound to hemoglobin, and only 2% of it is dissolved in the plasma. Well, this is opposite for carbon dioxide. So carbon dioxide is going to be built up during cellular respiration and then diffuses into the bloodstream. Only about 7% of the carbon dioxide is dissolved here. We do have movement of carbon dioxide into the red blood cell where it binds with hemoglobin. So about 23% of carbon dioxide is transported as carboxyhemoglobin, bound to hemoglobin. But then when we want to breathe it out, it needs to become unbound. So we have a chemical reaction using an enzyme called carbonic anhydrase that can break everything apart, allowing the production of bicarbonate, which moves to the plasma. This is how the majority of carbon dioxide is transported in our body. It is transported as bicarbonate in the plasma, 70% of it. Now, as the red blood cells move to the lungs, then we have the opportunity, let's run through this chemical equation. So now we've got too much acid, right? That's what we just built up because of the increase in carbon dioxide. So we can have essentially the reverse reaction where the acid, through the action of carbonic anhydrase, releases carbon dioxide from the hemoglobin, and then it moves to the bloodstream and can be expelled out of the body in the form of carbon dioxide through breathing out. So the majority of our carbon dioxide travels in our blood as the bicarbonate ion, 70% of it. The other 23 is bound to hemoglobin, and then the remaining 7 is dissolved as carbon dioxide. So we do see quite a big difference in how carbon dioxide and oxygen are transported. But the reason why carbon dioxide buildup can have such an impact on our blood pH is due to its relationship with carbonic anhydrase and how carbon dioxide and water produce acid. This is the same chemical reaction associated with the production of acid rain and the buildup of, and even in acidic springs. So acid rain happens when there's a buildup of carbon dioxide in the air. Well, there's a lot of water vapor in the air. So it's the same reaction that we just saw here. Water mixing with carbon dioxide produces acid, which if it's in the air can then rain down onto Earth. Okay, so putting it together with our exchange levels, exchange level 1 is between the atmosphere and the lungs. We begin with a partial pressure of oxygen at about 160 millimeters of mercury. We then move to exchange level 2 between the lungs to the bloodstream. We're at about 100 millimeters of mercury of oxygen. The majority of the oxygen is traveling within the safety of the red blood cell, bound to hemoglobin. Only about 2% of it is dissolved in the bloodstream. As the blood and the red blood cells make it to the tissue, then the oxygen is released from hemoglobin, and then it diffuses to the cells that need it for cellular respiration. That allows for the buildup of carbon dioxide, which then moves through exchange level 3 from the tissue back to the cells, and it stays at about the same pressure until we get back up to exchange level 2 between the blood and the lungs, and then finally out to the atmosphere. So the majority of oxygen travels as oxyhemoglobin, 98% of it. The majority of carbon dioxide travels as bicarbonate. Only 23% of it is attached to hemoglobin, and then 7% of it is dissolved in the plasma as dissolved CO2. We do have control centers in our brain, right? Breathing is really important. So we do have our respiratory control center that is located in the medulla of the brain, where it's nice and nestled into the structure and protected. And we know that there are changes. We began the chapter with this, that our control mechanisms respond to changes in oxygen, carbon dioxide, and pH. We have chemoreceptors in the brain, in the respiratory control center, in the medulla that respond to changes in carbon dioxide. They can perceive changes in pH because of the relationship between carbon dioxide in that watery environment. We also have chemoreceptors in the carotid vessels and in the aorta, and these are sensing all 3 variables. And then the integration of these signals into the respiratory control center in the brain are going to stimulate the various mechanisms to make corrections if one is needed. So we do see changes in, for example, if we see a buildup of CO2, then what that does is it's associated with an increased respiratory rate. Trying to get more oxygen in. Now, oops, I'm sorry about that. So looking at our control mechanisms, our long distance control mechanisms through the reflex, we're going to run through the different variables. So carbon dioxide triggers the chemoreceptors in the medulla, which then act on the respiratory control center to stimulate the muscles of inspiration or the muscles of expiration. We've got changes in molecular oxygen and pH that are read by the carotid and aortic chemoreceptors. These target the afferent sensory neurons, which are processed in the respiratory control center that then act on the muscles associated with expiration. Additionally, we have the limbic system, which is our emotion and voluntary control. These are processed in the medulla and the respiratory control center as well. That's the integrating center. But then they act upon the somatic muscles associated with inspiration, which would be the scalene sternocleidomastoids, the external intercostals, and the diaphragm. So we have a number of chemoreceptors that are present in different parts of the body that are constantly sensing the three variables of oxygen, carbon dioxide, and pH. So looking at how this works, the chemoreceptor response, in this case, we've got an increased concentration of carbon dioxide. So you can imagine this is me having an asthma attack. I can maintain my oxygen, but I build up CO2. So that's going to be picked up by the chemoreceptors that are present throughout that are present in the cerebral spinal fluid. So we have movement, we sense this increased pressure of carbon dioxide, which then through our chemical reaction with water and carbonic anhydrase makes the carbonate ion, which then dissociates into the hydrogen ion and the bicarbonate ion. So the hydrogen ion and the carbon dioxide are picked up by the chemoreceptor, which then feeds into the respiratory control center, which increases the respiratory rate. Additionally, we have the same pathway happening in the plasma because there is some carbon dioxide there. Well, that stimulates those peripheral chemoreceptors in the aorta as well as in the carotid vessels, and those target the sensory neurons, which feed into the integrating center. Additionally, a decrease in the concentration of oxygen to a certain critical level of 60 millimeters of mercury can also be picked up by these chemoreceptors, stimulating increased ventilation. So these pathways turn off through two negative feedback mechanisms. When we get an increase in the pressure of oxygen, that turns off the pathway that feeds into the peripheral chemoreceptors. Also, when we have a decrease in carbon dioxide, that's going to feed all the way up to the beginning of our reflex and turn it off by negative feedback. So we do have a number of reflective, protective reflexes to protect the lungs, right? We have a number of mechanisms that protect us from physical injury or the inhalation of irritants, or even from overinflating our lungs so they don't explode. Bronchoconstriction is part of a protective reflex, and it integrates into the control center. Sneezing is an example of another protective reflex. Goodness, I cannot say those two words together. Coughing is another. All right, so in our higher brain centers, there is an influence on the pattern of ventilation. That includes the hypothalamus and the cerebrum, and they're associated with changing breathing rate, as well as how deeply we breathe. Now, higher brain center control is not a requirement for ventilation. And this is how many people that have brain injury can be sustained on life support for a period of time. or even without life support for a period of time in a comatose setting. The limbic system, our emotions, certainly can take our breath away, right? We've all had that experience. I mean, if I told you right now in this lecture, hey, guess what? You're having an exam right before holiday tomorrow, that would probably trigger your limbic system in a not so pleasant way. You'd breathe faster and worry. Don't worry, that's not happening. Just trying to give you an example. The limbic system is actually capable of bypassing the control in our brainstem, but our brain centers can't override the chemoreceptors. So those chemoreceptors are constantly sensing pH, CO2, and O2. So in one way to think about it, they are the master control centers because nothing else can overcome them. All right, class, that finishes us up for the respiratory system. I hope that's helpful. I don't see my cat on the roof anymore, but I'm going to go find him. Take care, everybody. Stay well. Bye-bye.